All right, let's continue where we left off in example 11.5. So we were calculating the total angular momentum L, and we were summing up all of the individual angular momentums. And so we will get from this negative 30 k hat, and again it is in kilogram meters squared per second. Okay, so this is our total angular momentum. All right, so the last part of this is what is the rate of change of the angular momentum? Okay, so the rate of change of angular momentum is going to be the torque. So we want to find now the individual torques in each of these situations. Okay, so remember that torque is equal to the derivative with respect to t of L. Okay, and again the summation. And torque is going to be equal to R cross F, or R perpendicular F. Okay, so this is the form that we'll use to find our torque. Okay, so for our first one, we can go ahead and just look at it here. We have our force is in our I hat direction. Okay, so what we'll do is we will find our R perpendicular that's perpendicular to this F. So F is in the minus I hat. So our R should be in the J hat direction. Okay, so we're going to look at it in the J hat direction, which is going to be just one J hat. Okay, so if I go here, our summation of torques is going to be T1 plus T2, or tau. Tau 2, tau 3. Okay, so we've got our force, or R, sorry, which is 1, and it is J hat. Okay. And yeah, so 1 meter and then times minus 6 newtons. So this is in meters and this is in newtons. And so this is going to be in K hat. Okay. Plus our second torque. So we have our F is in the J hat direction. Okay. So we'll want our perpendicular, or our I hat piece, which is 4. So we have 4 meters and 10 newtons, again in K hat. And then our third one, we have F is in the J hat direction, so we want R in the I hat, which is 2. So we have 2 times, it was negative 8 newtons. This is meters again. And this is in the K hat direction. So we have negative 6 Newton meter plus 40 Newton meters minus 16 Newton meters, and this is all in the K hat direction. Okay, so let me go ahead and do that in the calculator. We have 40 minus 6 minus 16, and so we get the torque is equal to 18 Newton meters in the K hat direction. This is the sum of all torques. Whoops, got a little carried away with my summation sign. Okay. All right, so let's move on to angular momentum of a rigid body. Now, a rigid body is constrained to rotate about the z-axis with some angular velocity omega. Okay. This is made of small mass segments, delta m sub I, as we can see here, and they are located at some radius r sub I and have some velocity v sub I. Okay. I'm sorry, located at r sub I here. Okay, our position vector. Now this undergoes circular motion about the z-axis with the same angular velocity, omega. Since v sub I and r sub I are perpendicular to each other, the magnitude of the angular momentum of this mass segment is going to be L sub I equals r sub I delta m v sub I times sine of 90 degrees. Okay, so again we've got our r bar, our v bar, and so our L sub I bar is going to be in this direction here. Okay, and this is again the angular momentum vector of this mass segment, delta m sub I. Okay, from this we can also find the relation that the total angular momentum, big L, capital L, is equal to the moment of inertia I, times omega, the angular velocity. Okay, and instead of going through this example with you, I just want to point it out. See example 11.6. Let's go ahead and look at that. .6. And so this is really just going through finding moments of inertia and therefore the magnitude of the angular momentum. Okay, and same thing here. So it's kind of repetitive, didn't want to go through it, but just look at it, make sure you understand what is going on here. Okay. All right, and then we need to talk about the law of conservation of angular momentum. Okay, so this is where it gets a little interesting. So the angular momentum of a system of particles around a point in a fixed inertial frame is conserved if there is no net external torque around that point. Or we can say dl dt is equal to 0, or L is equal to a constant. Okay, the total angular momentum of a system is going to be constant. Okay, so take this figure skater for example. She has some angular momentum. Okay, as she has her hands out and her leg out here. Now when she pulls these limbs into her body, okay, she still has the same angular momentum, but now she'll have a different angular velocity and inertia. Okay, so, but the total angular momentum is constant. Okay, so it seems like, if you've ever watched figure skating, it seems like she's going faster, and that is because she has a larger angular velocity. Okay. Now let's take an example, 11.8. It states an 80-kilogram gymnast dismounts from a high bar. He starts the dismount at full extension, then tucks to complete a number of revolutions before landing. His moment of inertia when fully extended can be approximated as a rod of length 1.8 meters, and when in the tuck, a rod of half that length. Okay. If his rotation rate at full extension is 1 revolutions per second, and he enters the tuck when his center of mass is at 3 meters height, moving horizontally to the floor, how many revolutions can he execute if he comes out of the tuck at 1.8 meters height? Okay, that was a lot of information. I think we can agree. So we have this gymnast, and he is preparing to dismount, and as he dismounts, he tucks in, and then he lands. Okay? So, we're trying to find the number of revolutions that he can execute as he comes out of the tuck. So let's see. We know that the angular momentum has to be conserved. Okay, so before and after the tucking. Okay, so we should have L is equal to L bar. Okay, so we'll have I omega is equal to I bar omega bar. I'm sorry, apostrophe prime. That's what I'm saying. L prime, I prime omega prime. Okay. We have our rotation rate at full extension. So we have this omega. I is going to be approximated as a rod. So we'll have to look up that I. And same thing here. This is going to be 1/2 of I, this I with the rod. And then omega prime is what we need to figure out. Okay, so let me look up a couple of things, a couple of these I values, and then I will come back. Okay, so the inertia for a rod is 1/12 mL squared, where L is the length of the rod. Okay, not to be confused with the angular momentum over here. Okay, so what I had stated before, we'll have 1/2 L, not 1/2 the length of the rod, not 1/2 of I prime here. Okay, so let's go ahead and put these values in. We'll have I is going to equal 1/12 times our mass, which is 80 kilograms, times our length, which is 1.8 meters, and that is squared. Omega is 1 revolution per second. So I'm going to just write that here. Omega is 1 revolution per second. And we have I prime is equal to 1/12 times our mass, 80 kilograms, times our length of the rod divided by 2, which is going to be 0.9 meters squared. Okay. And I don't have, here's the tuck. Is at that height. Let's see. So we've got these two values, and I don't have my calculator again, so I have these two values, and from that we can put that into our equation here and solve for omega prime. Okay, so we want to solve for that, and so omega prime would be 4 revolutions per second.